Hi, I'm Herb Gross, and welcome once again to Gateways to Mathematics, where today we begin the final module of this particular course. Actually, this is the first time in the course where we'll be having two lectures, where one of which could actually be viewed as a continuation of the other, but we'll talk more about that in a while. I was trying to think of something humorous to think about as to how to open up this particular topic, and basically the only thing that could come to mind is a form of humor that was very common when I was in college and has since made a comeback on programs like the Johnny Carson Show. And that's the ones where somebody gives you the answer and you're supposed to make up the question. Remember those, like, if the answer is chicken sukiyaki, what was the question? And the question is, name the only living Japanese kamikaze pilot. If the question is 9W, if the answer is 9W, the question is, do you spell your last name with a V, Herr Wagner? And I like these little funny stories because this is exactly what the relationship is between arithmetic and algebra. That basically the difference between starting with the question and giving the answer and starting with the answer and reconstructing the question is one way to look at how arithmetic and algebra are related. And that's what I'd like to discuss with you in our session today. So let's go over to the board. And let me just pick a hypothetical situation with you. Let's suppose I'm a geography teacher, and I want to test to see if my class knows that Sacramento is the capital of California. And the way I'm going to test is by filling in the blank, okay? So I say, blank is the capital of California. You see what I've done here is I've left out the name Sacramento and replaced it by a blank. Now, of course, I could have worded the problem differently. I could have left out California and put in Sacramento. I could have said Sacramento is the capital of blank. Both of these statements, when filled in correctly, are going to say what? Sacramento is the capital of California. But do you notice that one of these two forms is psychologically easier to answer? See, look at the idea here. In this particular form, the only proper noun you see is California. And when you see California, you don't necessarily think of Sacramento. You might think of San Diego, you might think of Los Angeles, San Francisco, a whole bunch of places, but not necessarily Sacramento. On the other hand, when you see Sacramento as the capital of blank, you say, gee, I didn't know that Sacramento was the capital of anything. But seeing as it's in California, I think it's a pretty good bet that that's what it's the capital of. So my guess is, if two teachers were testing their class on the same information, and one gave the question in the form of 1 and the other in the form of 2, the teacher who gave it in the form of 2 would have looked like the smarter teacher because her class would have scored higher on this. By the way, there's a third version that's much more complicated, and that is you leave the two nouns, the two proper nouns in, but you leave out the non-proper noun. In other words, what you could also have said was what? Put in Sacramento and California, leave out the word capital, and say Sacramento is the blank of California. And now what this does is something that we're going to be very interested in. This forces the student to derive a relationship between Sacramento and California, where the relationship in this case is the capital of. Now, what does all this have to do with mathematics? And the answer is that in the same way that forms 1 and 2 here were two different ways of seeing whether a student knew that Sacramento was the capital of California, we also do the same thing in arithmetic. Look, let's suppose the same arithmetic teacher now wants to test to see if the student knows that 8 plus 3 is 11. One way of wording the question is to say 8 plus 3 equals blank. Another way of wording the same question is to say 8 plus blank equals 11. In both cases, when the blank is filled in properly, we have 8 plus 3 equals 11. But notice that psychologically, the first one is probably easier for the student than the second one, because the first one looks like an addition problem, and it is an addition problem. The second one looks like an addition problem, but it's really a subtraction problem. In fact, if you had a calculator and didn't even know what addition meant, you could do the first problem just by saying what? 8 plus 3 equals, and the answer would light up. But you couldn't do the second one that way. And you may recall in our last lecture, I mentioned to you that one difference between arithmetic and algebra in terms of a calculator was that if you can do the whole problem just by reading it directly with no translation and get the answer on the calculator, that's arithmetic. But if you have to do some inversions, that's algebra. Now, there are a few things that we do in algebra that are a little bit different than fill in the blank. For one thing, we don't usually use the blank. It's not important as to why we don't use the blank. That will become clearer as we go along. Usually we use a letter of the alphabet to stand for the blank. A typical algebra problem might look like this. Find the value of p if 8 plus p equals 11. And you know, so many times in this course, we have talked about a second language. And one of the reasons that mathematics is hard is for the same reason that it's hard to keep track of what's going on in soap operas sometimes. There are so many subplots going on that it's hard to keep track of the main action. There are so many different languages taking place within mathematics that it's hard to become, you don't have to be bilingual or trilingual. There's probably about 15 different languages that you sometimes are keeping track of in one course. And basically, you see, when you say find the value of p, if 8 plus p is 11, can you visualize the person that says p is a letter of the alphabet? It's not a number. But p is used here the same way as the blank is used here. In other words, when you say find the value of p when 8 plus p is 11, that's the same as saying fill in the blank, 8 plus blank equals 11. The part that's interesting about algebra is that we use a new strategy. You see, up until now, I've been trying to teach you that when you see 8 plus blank equals 11, you have to remember that that means what? Blank equals 11 minus 8. Just like we introduced dimensional analysis to find an easy way to keep track of things, algebra does the same thing for us. See, what we say in algebra is something like this. We would like the value of p. What keeps p from being all by itself on this side of the equal sign? The 8. What's the 8 doing to the p? It's being added to the p. How do you get rid of adding 8? You subtract 8. But the equal sign is like a seesaw. It's balanced. If you subtract 8 from one side, you have to subtract 8 from the other side. Now what happens? 8 minus 8 is 0. 0 plus p is still p. And 11 minus 8 is 3. I don't know if you noticed the mechanical beauty of this, but notice in this particular form, all you had to do was see what you had to do to get p by itself. Whatever you did on one side, you just mechanically did that on the other side of the equal sign, and the answer takes care of itself. Now, when the two numbers that you want to add are both on the same side of the equal sign, we say that also differently in algebra. Instead of saying things like, how much is 8 plus 7, we might say something like this. I just want you to get used to the vocabulary. Evaluate 8 plus m when m is 7. See, how do we know if m stands for a number? How do we know what 8 plus m is? See, all 8 plus m tells us is that we have 8 more than whatever the value of m is. So what this problem says is, what will 8 plus m be when m is 7? And all that means is you write down the expression 8 plus m, replace m by 7, and do the resulting arithmetic. And do you see why I call that an arithmetic problem? Because now all you have to do is what? Exactly what you see. 8 plus 7 is 15. Well, we don't always add. So we can do other operations. And the name of the letter also isn't very important. Let me give you another example. Evaluate 7 times t when t equals 4. See, what this says is t stands for a number, and what are you going to do that number? You're going to multiply it by 7. What will the answer be? The answer depends on what t is. And I'm going to show you another interpretation of that in a short while. But for the time being, all you have to do is be blindly obedient. All this says is evaluate 7 times t when t is 4. So all you do is you take t, replace it by 4. When t is replaced by 4, this reads what? 7 times 4, which is 28. Okay? Now, there is one agreement that we make. You see, when we write the letter x, we don't know whether it's a letter of the alphabet or whether it's a time sign. And usually it's clear from context which one you mean. But if we're going to use letters of the alphabet to stand for numbers, then the x becomes confusing. So the agreement that we make is, because x looks like a letter of the alphabet, we prefer to write 7t. See, the 7 is just next to the t here, or else you put the t in parentheses to emphasize it, rather than 7 times t. Now, I don't know if this makes sense to you, but there is an easy way to remember this. I don't know if you ever thought about it this way. Suppose I write down 7 apples. What arithmetic problem is implied by this phrase? Do you know? You say, what do you mean arithmetic problem? I'm just counting the number of apples. No, this can be viewed as a multiplication problem. See, you have 7 apples. That means you have what? 1 apple 7 times. See, 7 apples is what? An apple 7 times. See, we're already assuming that when a letter stands next to the, when a number stands next to the noun, it's already a form of multiplication. See, 3 pencils is 1 pencil 3 times. But I'm not going to get into that. I just want you to visualize that particular idea. So in other words, when I say evaluate 8q when q equals 6, that means to replace q by 6. But what does 8q mean? See, 8q means 8 times q. So all you do is replace the q by 6, and the answer is 48. The reason I cringe about teaching this is if you really wanted to be technical, can you visualize a student not knowing any better and in good faith saying something like, I'll replace q by 6. And now the answer is 86. See, the point I want you to see is that this is not a place value numeral. When a number appears next to a letter, that's an abbreviation for multiplication. In an arithmetic problem with letters, if no arithmetic symbol appears, it's understood to be multiplication. Now, once you learn this, you still have problems. The same old problem that we always have, namely reading comprehension. See, in this problem, I said, find the value, evaluate 8q when q is 6. See, that's not an algebra problem. Watch where the algebra comes in. In problem number 5, I say, find the value of q if 8q equals 40. See, if 8q equals 40, how much is q? Well, remember, 8q means 8 times q. The q is a letter that takes the place of a number, so it's really a glorified blank. So this looks like what? 8 times blank equals 40. This looks like a multiplication problem, but it's really what? Division, so the answer is 40 divided by 8, and that would be q, okay? Now watch how the algebra works here. See, again, in this form here, you say, look, the thing I want is q by itself. What's blocking the q? What keeps the q from being all by itself over here? It's the 8, isn't it? What's the 8 doing to the q? Since there's no arithmetic sign between the 8 and the q, the 8 is multiplying the q. How do you undo multiplying by 8? You divide by 8. If you start with 2, multiply by 8, then divide by 8, you're back to 2 again. See, to undo multiplying by 8, you're going to divide by 8. And in terms of the language of common fractions, that means you put 8 in the denominator. But this is still a seesaw, isn't it? It's balanced. If I divide by 8 on one side, I have to divide by 8 on the other side. The 8's now cancel. I wind up with q on this side. 40 over 8 means 40 divided by 8, which is 5. And you see that all we're doing so far is discovering a new language for doing the same things that we were always doing. And by the way, I want to emphasize this new language to you because it's quite powerful. I want you to learn to use it. It's a very simple thing to use, but it still requires reading comprehension. I want you to notice the difference between whether the 8 is multiplying the q or whether the 8 is being added to the q. See, problem number 6 says, find the value of q if 8 plus q is 40. And in terms of fill in the blank, replace the q by a blank. That says 8 plus blank equals 40. What's the value of the blank? So doing it the way we were doing it before this lecture, you would say this looks like an addition problem, but it's really a subtraction problem, and the answer is 40 minus 8, which is 32. But the algebra way doesn't even make you think that much. What it says is, look, you want the q by itself. What's blocking the q from being by itself? The 8. What's the 8 doing? It's being added to the q. See, you have to still read. How do you undo adding 8? You subtract 8. But if you subtract 8 from one part of the balance, you have to subtract 8 from the other part of the balance. The 8's drop out. You wind up with q equals what? 40 minus 8, which is 32. And that's precisely the same reasoning that you used before. See, so are you with me so far? Now, the reason I'm leading into this is that we're going to, do you all know that old story? I think it's an Aesop fable. 7 blind men go up to an elephant, and they each touch a different part of the elephant. And based on what part each man touches, they give a completely different description of the elephant. So each man is partly correct, but no one is really right. And the moral of the story is that sometimes one greater truth encompasses several lesser truths. And the same thing happens when you try to define mathematics. Mathematics, for justifiable reasons, means different things to different people. There is no short, pithy phrase that you can give in 25 words or less that defines what mathematics really is. But there are standard uses of mathematics that are very, very important. And one of the definitions of mathematics that's used very often in technology, in science, in lots of places, is that mathematics, and here's a big word in here, but don't worry about it, is the quantitative study of relationships. See, in mathematics, not only do you study relationships, but you measure them. For example, if I were to take this pen, and the producer makes me pay for all the ones I break, so I'm just going to pretend to do this one. If I take this pen and I drop it, it doesn't take much insight to see that as that pen falls, it falls faster and faster. See, so if you say, hey, the pen falls faster and faster, that's not what we mean by the quantitative study of relationships. The quantitative study of relationships says, okay, at a given time, how fast will the pen be falling? See, what is the formula that will relate the time that the pen has been falling to how fast it's falling? That's what we mean by the quantitative study of relationships. So if you have studied any subject in which you have seen a graph, you have studied the quantitative relationship between various concepts. And that's the thing that we're going to emphasize here. And let me start off in a way that shouldn't frighten you. I'm going to start off with what I call just a verbal situation. I say to you, I don't know what number I want you to pick, so I'll just call it P. I say start with some number P. Well, what number is P? It's whatever number you want to start with. You start with P. I say to you, multiply by 3. Then I say add 5, and I say whatever answer you get, you call that C. Now, how hard a problem is this? For example, suppose I start with 7. I pick P to be 7. I multiply by 3, what do I get? 21. I add 5, I get 26. So if I start with 7, the answer is 26. Is there anybody who had trouble following me do that? Of course not. You just read this thing. You might say, what made you pick 7? Why didn't you pick 11? Could I have picked 11 if I wanted to? If I started with 11, I multiply by 3 gives me 33. I add 5 gives me 38. And so now the answer would be 38. Well, so what? You see, obviously, I get a different answer depending on what number I began with. But the important thing is, there's nothing threatening about this, is there? See, let me give you some insight here. You say, who would ever play a game like this? Didn't you do this when you were little kids? These little number riddles. Pick a number, add 2, multiply by 3, subtract 4, add your father's age, what's your answer? Then you tell the person how old their father is. Well, we're not doing it for that reason here. What I want you to see is that this is precisely how the study of relationships is done. Let's suppose you're ordering cheese from a cheese catalog, and the catalog says something like this: $3 a pound plus $5 for shipping and handling. Suppose you wanted to buy 7 pounds of cheese. Under the command, it's going to be $3 a pound plus $5 for shipping and handling. How do you figure out what it's going to cost you? You start with the number of pounds. I even picked P to stand for pounds. How many pounds did you pick? 7. You multiply by 3 because it's $3 a pound, isn't it? So 7 pounds are going to cost you $21. Then you add 5 because that's the shipping and handling charge. So if you're going to buy 7 pounds of cheese from this catalog, it's going to cost you $26. What if you want to buy 11 pounds of cheese? 11 times 3 is 33, plus 5 is 38, isn't it? You see, this may look like just an empty formula, but what problem does it solve? That doesn't sound that glorious, but the cheese problem. How much will P pounds of cheese cost? See, P for pounds, C for cost, if it's $3 a pound and $5 for shipping and handling. Okay? But the interesting thing is, we can think of this in terms of a computer now. See, what we can think of, what's the computer language? You have an input, you have an output, and you have a program. This will be called the multiply by 3 and add 5 program. Basically, you make the input. Whatever input comes into the machine, what does the machine do? It multiplies by 3, it adds 5, and it gives you the output. And quite frankly, as far as this course is concerned, the only difference between arithmetic and algebra in terms of this analogy is when you have the input and the program, the process of finding the output is arithmetic. If they give you the output and the program and you try to find the input, that's called algebra. And I'll give you more experience with that as we go along. But the point is that algebra writes things in its own language. Isn't it kind of cumbersome to say things like start with P, multiply by 3, add 5, the answer is C. So we use our own language in algebra. What we say is, okay, take the number you're going to start with, that's P, isn't it? Multiply by 3, well, that's P times 3. Then we put this in parentheses to indicate that that's now our new answer. See, that's one. Remember, everything inside the parentheses is one number. Then what'd you do next? You added 5. Then you said, and the answer is, the equal sign takes the place of the word is. The answer is C. In other words, starting with this, the way you read this is, pick a number, which we'll call P, multiply by 3. See, where do you know where the pick a number is? It's the one that's messed up with all the numbers. The answer is the letter that stands all by itself. So I look for the letter that's all messed up with the numbers here. I remember that everything inside the parentheses is done first. So I first find P. It's inside the parentheses, so that tells me to multiply by 3. Then I'm told to add 5, and the answer is C. And by the way, we make shortcuts within shortcuts. A couple of things happen. For some reason, which to this day I still don't fully understand, the answer always is given on the left-hand side. In other words, instead of the C being over here, it usually appears over here. Secondly, instead of saying P times 3, you usually say 3 times P, in much the same way as you usually say, give me 3 apples, rather than give me apples 3. And the second thing is, we agreed what? That the multiplication symbol is left out. So this is now an abbreviation for what? Start with P, multiply by 3, and when that's all done, you add 5. And to make even more of an abbreviation, the agreement usually is, if you leave out the grouping symbols, they're understood to be dictated by the plus signs. In other words, if I don't see a grouping symbol here, the plus sign tells me to do this. But I'm not going to make too big an issue over that. What I want to do is to make sure you can read this notation. See, here's where I want you to become to be bilingual. I will call this an algebraic formula. And what I want you to learn to do is how to translate between, well, let's put it this way. Given the algebraic formula, how do you read it verbally? And given the verbal formula, how do you rewrite it algebraically? And there's lots of practice involving that in the book. But let's just go through a little bit of this together. See, if C equals 3P plus 5, find the value of C when P is 20. Basically, all that says is start with this formula. Every place you see a P, replace it by 20, and see what's going to happen here. See, what happens over here is, if I start with 20, see, 3 times 20 is 60. 60 plus 5 is 65. So the answer would be 65. And what that means is, if I were buying 20 pounds of cheese at $3 a pound and $5 for shipping and handling, it would cost me $65. Now watch the reversal of this. Problem 8 looks an awful lot like problem 7, but it's really quite different. It says, if C equals 3P plus 5, find the value of P if C is 20. You see, what I do now is, I give you the value of C and ask you to find the value of P. And the way this game is played by algebra, here's what you do. You want to get P all by itself. The parentheses is protecting the P. In other words, to get at the P, you first have to get at the parentheses. But what's blocking the parentheses? The 5. So what you're going to do is, to get rid of adding 5, you subtract 5. And if you subtract 5 from one side, you have to subtract 5 from the other side. That tells you that 15 is equal to 3 times P. Now you're inside the parentheses. You want P by itself. The P is being multiplied by 3. To undo multiplying by 3, you divide by 3. And if you divide by 3 on one side, you also have to divide by 3 on the other side, and that gives you what? 15 over 3 is 5, so p must be 5. And by the way, if you don't believe this, you can always go back and check. If you put 5 in here, 5 times 3 is 15, 15 plus 5 is 20, and that was the correct information. By the way, when you put the 5 in here, the reason you say 3 times 5 first and not 5 plus 5 is everything inside the parentheses has to be done first. Now, a lot of people have trouble with this, and I just wanted to show you what this thing says. In other words, I am going to recapitulate problems 7 and 8 from the verbal point of view. See, from the verbal point of view, the formula was what? Start with p, multiply by 3, add 5, and the answer is C. In problem number 7, we were told to start with 20 and see what the answer would be. See, start with p being 20 and see what C is. What do you do here? Just read it. 20 times 3 is 60, plus 5 is 65, so the answer is 65. See, going in this direction, it's straightforward arithmetic. Problem 8 said if the answer is 20, what did you start with? Now, this is tricky, but I think it's really neat. You start with 20. When did you have the 20? After you added the 5. Therefore, what did you have before you added the 5? Starting with the 20, since that was what you had after you added 5, you do what when you reverse the steps? Subtract 5. See, when you work backwards, wherever you see add, you're going to put subtract and vice versa. Multiply gets replaced by divide, etc. So watch what we do here. We start with 20. Now, instead of adding 5, we're going to subtract 5. That gives us 15. Now, instead of multiplying by 3, see, we're going this way, we divide by 3. That gives us 5. So it means p must have been 5. And does that check with our previous answer? Sure it does. And look at 5 times 3 is 15, plus 5 is 20. See, arithmetic was when you started with the number of pounds and found the cost. That's when you say, gee, I want to buy 20 pounds. How much is it going to cost me? The algebra was when you said, hey, all I've got is $20 to spend. How many pounds can I buy? See, arithmetic was starting with the 20 and getting 65. Algebra is when you started with the answer. See, we start with the answer and make up the question. Do you sort of get the idea of what's going on here? We're going to do lots more of this in the text and in our lecture, but I just want you to get used to this. And I want you to get used to just reading things this way. Look at problem number 9. It says, using the information below, find the value of p. Now, what's the information below? It says start with p, multiply by 2, add 3, and the answer is 151. How do I find p from this? I know when I'm all through, I had 151. When did I have the 151? Right after I added the 3. So therefore, what must I do to reconstruct what happened? I subtract 3. That gives me 148. When did I have the 148? After I multiplied by 2. So to find out what I had before, I divide by 2. You see what I'm saying here? This says blank times 2 is 148. So to find the value of the blank, I'm going to divide by 2. See, it says multiply by 2, but when I'm reversing the steps, I'm going to have to do what? Divide by 2. 148 divided by 2 is 74. So that means that if I wound up with 151, I must have started with 74. And let's check it. 74 times 2 is 148. Big surprise, we already knew that. And 48 plus 3 is 151. Believe it or not, going from bottom to top, as opposed from top to bottom, is all algebra is all about. Now, by the way, you see, what other people do with this, let me show you how this becomes a traditional algebra. You're starting with p, then you're multiplying that by 2. We write that as 2p. Then you're adding on 3, and the answer is 151. So now when we write that algebraically, we say 2p, in parentheses, plus 3 equals 151. Do you see how to read that? Look for the letter. Do everything inside the parentheses first. That says start with p, multiply by 2, add 3. The answer is 151. Now the job is how do you find out what p is? And we do exactly what we did in the verbal form. In other words, the p is inside the parentheses, so it's being protected. What's it being blocked by? The 3. What's the 3 doing? The 3 is being added to undo adding 3, you subtract 3. But if you subtract 3 from one side, you also have to subtract 3 from the other side. So now you have 2 times p is 148. You want p by itself. The 2 is spoiling that. What's the 2 doing? It's multiplying the p. So to get rid of it, you divide by 2. If you divide by 2 on one side, you have to divide by 2 on the other side. So the answer is 74. And again, for people who think that algebra is just meant as a mental exercise, which, by the way, wouldn't be the worst thing in the world either. You know, people sometimes say to me, where am I going to use algebra in the real world? Well, if he's a ball player, I say, tell me, you're a football player. I've said this to my own son. Show me once in a football game where you do push-ups. He says, Dad, we don't do push-ups in a football game. I say, so why do you practice them? He says, because the push-ups give me the strength to do what I'm supposed to do in the game. Well, you see, algebra is to the world of computation and science what calisthenics are to the athlete. The algebra teaches you the mental alertness, the skills that one needs to solve the problems in the real world. Okay? That's the only motivation I have to give you. But the important point is, look at this problem here. A catalog office candy at $2 per pound, plus $3 for shipping and handling. How many pounds can you buy for $151? That's exactly the problem we just solved over here. You see, what's this? The number of pounds is p. 2 times p plus 3 equals 151. See, that's why I want you to have some skill with this. And let's just practice one more to see if you've got the knack of this. Number 11 says, translate the following. 2, open parentheses, see, start the parentheses, p plus 3, see, c equals 2, open parentheses, p plus 3, close parentheses, translate that into a verbal formula. Now, what's the trick to this? Look for the letter that's scrambled with the numbers. See, the letter that stands by itself, that's going to be the answer. So you go over here, and now you've found the p. So what are you going to do? You're going to start with p. Look inside the parentheses. What's the first thing that's being done? You're adding 3, aren't you? So the next step says what? You start with p, then you add 3. What do you do after you add the 3? There's a 2 outside the parentheses. What's the 2 doing? There's no arithmetic symbol, so it must be what? Multiplication. So what do we do next? We multiply by 2. And be very careful about this. See, don't say, oh, I think I'll multiply by 2 first. Remember, everything in the parentheses has to be done first. And so you're going to add the 3 first. In fact, if you multiply by 2 first and then add the 3, isn't that the candy problem we just did? I don't know if you realize that, but if you change the order of steps 2 and 3, you also change the answer. Look, suppose I started with 8 here. If first I add 3 and then I multiply by 2, what will I get? 8 plus 3 is 11, multiplied by 2 is 16, is that right? No. 8 plus 3 is 11, multiplied by 2 is 22. Now suppose I reverse the steps. 8 multiplied by 2 is 16, plus 3 is 19. In other words, if I go this way, the answer is 19. Why does it make a difference? Because in this case, once I add the 3 on, it's also being multiplied by the 2. So the order of the steps here is very important. But I want you to learn to just play around with this stuff. So in other words, that verbal formula states what? C equals twice p plus 3. Now, if I said to you, find the value of c if p is 74, all you're going to do is what? Replace p by 74 over here. Then you do everything inside the parentheses first. You say 74 plus 3 is 77. 2 times 77 is 154. And isn't that exactly what you'd be doing over here? If you start with 74, you add 3 gives you 77, multiplied by 2 gives you 154. Now, suppose we reverse the process. Suppose I give you the answer first, then I ask you to find the question. See, problem number 13 says, if c is equal to twice the quantity, p plus 3, find the value of p when c is 50. So you replace c by 50, now you have to find the value of p. This is tricky. I'm going to show you some things over here. First of all, everything inside the parentheses is sacred. You don't touch the parentheses till you unblock it. What's blocking the parentheses here? The 2. What's the 2 doing? It's multiplying the parentheses. So to undo it, we're going to divide by 2. But if you divide by 2 on one side, you have to divide by 2 on the other side. 50 divided by 2 is 25. If 25 is p plus 3, what keeps the p from being by itself now? The 3. What's the 3 doing? It's being added. To undo adding 3, you subtract 3. But if you subtract 3 from one side, you also have to subtract 3 from the other side. That gives you that p is equal to 22. And by the way, if we can just come back to the other board for a second, I'd like to show you that as abstract as this looks, that's exactly what you were doing over here. Look, suppose I say to you, start with p, add 3, multiply by 2, and the answer is c. To say replace c by 50 means this. Let's go and reverse our steps. We start with 50. As we work backwards, instead of multiplying by 2, we're going to divide by 2. That gives us the same 25 that we had over here. Now it says what? Add 3, but we're reversing the steps. So instead of adding 3, we're going to subtract 3, and there's the same 22 that we got this way. And remember, nice versus necessary. A lot of people will tackle this problem and they say, well, I'm going to do it a different way. Since the 3 is being added to the p, I'm going to subtract the 3. I just told you that whatever is inside the parentheses is being protected by the 2. Let me show you what happens here. If you subtract 3 from 50, you get 47. That's fine. Here's the trick over here. This is not really a 3, because by a distributive property, isn't the 2 multiplying both the p and the 3? See, this is really 2p times 2 3s. You can't just cancel the 3's this way. This is really what? 2 times 3 is 6. And when you subtract 3 from 6, you're still going to have 3. You see, you've got to be very careful here. If you do want to get rid of the parentheses, you can use the distributive property and say this is the same as 2p plus 6. Then you can subtract 6 from both sides to get 44, then divide both sides by 2 to get 22. But again, we're going to have lots of practice with that. And the other thing that I wanted to show you that I think is real fun this way is how complicated problems can be done one step at a time. Here's a very complicated recipe. I don't even know if we can get it into one shot, but it doesn't matter. It says start with x, add 4, multiply by 6, subtract 3, multiply by 2, subtract 18, divide by 12, and the answer is y. And problem number 14 says, referring to this whole list of commands, see, referring to that verbal formula, what is y when x is 7? So what do we do here? We just replace x by 7 and do what we're told. 7 plus 4 is 11. Multiply by 6 is 66. Subtract 3 gives me 63. Multiply by 2 gives me 126. Subtract 18. I hope I don't make too many careless mistakes over here. That gives me 108. Divide by 12. That gives me 9. So if I start with 7, the answer is 9. Not 9 like in no, 9 like in 9, okay? Now, the reverse problem says, referring to the same formula, verbal formula, what is x if y is 7? That says now you're starting with 7 and you want to find out, in other words, if the answer was 7, what was the question? And as complicated as this looks, if you just take your time and don't panic, you can reconstruct this thing. See, when did you get to 7? After you divided by 12. So to undo this, you're going to do what? Multiply. See, going this way, you're just going to do you're going to do the inverse operation. Instead of dividing by 12, you're going to multiply by 12. 7 times 12 is 84. Instead of subtracting 18, you're going to add 18. 84 plus 18 is 102. Instead of multiplying by 2, you're going to divide by 2. 102 divided by 2 is 51. Instead of subtracting 3, you're going to add 3. 51 plus 3 is 54. Instead of multiplying by 6, you're going to divide by 6. Is that right? 54 divided by 6 is 9. Okay, that 9 keeps coming up again. I picked a good joke at the beginning today. 9. Yeah, 9. Okay, now instead of adding 4, I'm going to subtract 4. So the answer is 5, isn't it? Let's check it. If I started with 5, what would happen here? 5 plus 4 is 9. 9 times 6 is 54. 54 take away 3 is 51. 51 times 2 is 102. Subtract 18. gives me 84. Divide by 12 gives me 7. I'm back to what I'm supposed to have. And by the way, do you notice that if you read down this column, you get exactly the same numbers that you constructed when you read up this column? See, reading from top to bottom is arithmetic. Reading from bottom to top is algebra. And by the way, for those of you who are frightened by what I'm doing, close your eyes, and I'll tell you when to open them again. But for those of you who find this exciting, I'd like to show you another thing that algebra does. It's called paraphrasing. It's something that's typical of the world of technology today. See, after you solve a problem, the next question to ask is the solution too cumbersome? Is there a neater way of doing it? See, could we have taken all of these wires that solve the problem and used fewer wires? Let me show you how this works, if you can bear with me. And as I say, if you can't bear with me, I'm going to stop in about 2 minutes. See, I start with x, so we call that x. Now I add 4. That's x plus 4. What do I do next? I multiply by 6. But by the distributive property, that's 6x plus 24. The next step says subtract 3. Notice I don't subtract the 3 from the 6, because the 6 is modifying x's. I subtract the 3 from the 24. That's 6x plus 21. What do I do after I subtracted the 3? I multiply by 2. Using the distributive property, that's 12x plus 42. And by the way, if this seems hard for you, don't worry about it. That's what algebra is all about. If the only thing there was to algebra is what I'm showing you in Module 12, we'd be all through with all the courses. But anyway, let's just go on over here. After we multiply by 2, we're going to subtract 18. See, not from the 12x, but from the 42. That gives me 24 over here. That's 12x plus 24. Now what I'm going to do is to divide by 12, but dividing by 12 is the same as multiplying by 1/12. Use the distributive property again. 1/12 times 12x is x, and 1/12 of 24 is 2. And when I get all done over here, look what I have. My input was x. My output was what? X plus 2. What simple command is x plus 2? Pick a number and add 2. I don't know if anybody picked this up, but do we have a second to go back to this? Look what happened over here. When we started with 7 and we went through all these steps, what was the answer? 9. It was the same as all we did was take the 7 and add it on 2. When we started with 5, what was the answer? 7. In other words, all these steps could have all been replaced by what? This whole mess could have all been replaced by the add 2 program. And that's another aspect of algebra. It's like a language. The University of North Carolina, I don't know if they still do it, but at one time the University of North Carolina, as part of the language requirement, the foreign language requirement, allowed students to fulfill the foreign language requirement by taking calculus. Because their feeling was, if you can get through the language of mathematics, that's every bit as valid an experience from a structural point of view as going through a regular, traditional type of language. And that's one of the things that algebra helps us do. It wasn't invented to make things harder for human beings. It was invented to be the servant of people, but tradition has made us its servant. But enough about that. Let me just go through one more formula with you, and then I'll summarize how far we've come so far. You see, we haven't done that much, but we've broken new ground. And when you break new ground, it doesn't take long to become saturated. So I don't want to do too much at one time, but I do think I would like to do one formula for you that isn't that hard to handle, but plays a very important role in the metric English system. Here's a formula. I'll use computer language. Input f. So you start with a number f. First step is to subtract 32. Then you're going to multiply by 5. Then you're going to divide by 9. And the answer is going to be called C. Let me see if I can give you an example of that. Suppose I start with 77. I subtract 32. That gives me what? 45. Now I multiply by 5. That gives me 225. Now I divide by 9. That's 2, remainder of 4, that's 25. So the answer is 25. Oh, by the way, for those of you who have become veterans, what do you call the process where when you multiply by 5 and divide by 9? What one step is it when you multiply by 5 and divide by 9? Have you all become seasoned veterans in my campaign? Remember we said at the beginning that fractions were just another language for saying things that were easier to say without fractions? Like instead of saying, give me 2/3, you say 2 for me, 1 for you, 2 for me, 1 for you. When you multiply by 5 and divide by 9, isn't that the same as the one step that says multiply by 5/9? You multiply by the numerator and divide by the denominator. In any event, let's see if we can write that formula in algebraic form. See, we start with f. The first step says what? Subtract 32. Then we're going to do what? Multiply by 5 and divide by 9. That's the same as multiplying by 5/9. And you see why I put the parentheses here? Because I don't multiply by 5/9 until after I've subtracted the 32. And then we said what? Whenever you're multiplying, you put the multiplier, the numerical multiplier, to the left, and you leave out the time sign. So now it looks like what? C equals 5/9 f minus 32. Look at this and compare that with the formula that I wrote down over here. Do you see the psychological difference? This is wordy, but it's easy to understand. This is compact, but if you're afraid of mathematical symbols, it frightens you. But the thing I want you to see is that these say the same thing. You see, look at, start looking over here. Find the variable. You start with f. See, it's all mixed up here. Do what's inside the parentheses first. Subtract 32. Then what do? Multiply by 5/9, and the answer is C. Let's go through one more problem together using this form. If C is equal to 5/9 of f minus 32, find C if f is 68. By the way, we sometimes use stupid language in math. I mean, I've had students say to me, I say to students, find C. The kid says, here it is, I found it. No, when I say find C, it means what is the value of C when f is 68. What do I do over here? I just replace the f by 68. 68 minus 32 is 36. 5/9 of 36 is 20. So when f is 68, C is 20. And by the way, that's exactly the same thing I would have done verbally. You see, I would start with f, subtract 32, multiply by 5, divide by 9, I would get 20. This may seem like a not so fun formula. Does anybody happen to know out there what formula this is? Right, Ani, what? It's converting Fahrenheit to Celsius. That's what the teacher said to the kid. If it's 68 degrees in Fahrenheit, what's the temperature in Celsius? And he said, how far is it from Celsius to Fahrenheit? See, the weather changes as you go from one town to another. No, what this, and I'm going to show you this in the enrichment lecture, but basically what this procedure has shown was that when the Fahrenheit temperature is 68, the Celsius temperature is 20. And the beauty of that is, do you have to know why this formula works to be able to use it? No. But if you know why it works, it makes you doubly enriched. And what our final lecture is going to be about is to show you how one uses formulas even though one may not know how to derive them. And I'm going to show you how certain formulas were derived, including this one. See, the inverse of this problem is you start with the same formula. If C is 5/9 of f minus 32, find f when C is 20. In other words, now you're starting with the C being 20, and you've got to figure out what the f is. You see, it's the same old stuff again. To get at the f is inside the parentheses. To unblock the parentheses, you have to get rid of the 5/9. The 5/9 is multiplying the parentheses, so to get rid of multiplying by 5/9, you have to divide by 5/9. But you should know by now that what? Dividing by 5/9 is the same as multiplying by 9/5. And if you multiply by 9/5 on one side, you also have to multiply by 9/5 on the other. 9/5 of 20, see 20 divided by 5 is 4. 4 times 9 is 36. So f minus 32 is 36. To find f by itself, you now have to do what? Get rid of the 32. Since the 32 is being subtracted, you have to add it. If you add 32 to one side, you have to add 32 to the other. And now you've done the inverse problem where you've shown that if the Fahrenheit temperature is 20, if the Celsius temperature is 20, the Fahrenheit temperature had to be 68. Now, what I would suggest doing at this stage, in fact, I've written it down here. Maybe it's better if you see it on the board here. The next enrichment lecture can be viewed any time during this module. In a sense, it's like, even though the study guide doesn't say it, it's really a continuation of this lecture, only it expands what we've been saying here. I prefer that you go to the textbook and study Module 12 through example 20. That will take you through the mechanical applications of Celsius and Fahrenheit that I've just talked about. And I want you to practice on that until you feel comfortable with it. Then we'll come back to our final enrichment lecture, and we'll discuss some of the fine points. But what I'm hoping that you're seeing right now is that if you've been taking this course one step at a time, the transition from arithmetic to algebra is no more complicated than the process of saying, if I'm given the input and the program, I can find the output. That's arithmetic. If I'm given the output and the program, and I go and reconstruct the input, that's algebra. That's the only difference between the two. So in terms of a verbal formula, where you start with something and finish with something, arithmetic is when you start at the top and go to the bottom. Algebra is when you go from the bottom to the top, coupled with the fact, as I showed you in one problem, that algebra is a fantastic technique for paraphrasing, for taking complicated lists of commands and condensing them into simpler equivalent commands. At any rate, that's enough for today. With our usual advice, what do I tell you now? You should at least know this much from the course. How am I going to end? Study hard, have fun, and stay young.